time for us to do some practice involving changing order of integration, which really at its heart says we're going to work on understanding our geometry. It's one of the things that makes multivariable calculus so much fun, is we really get to test our geometrical knowledge and understanding. And in this case, saying, can you go from bounds to picture and from picture to bounds? Now, the way you do this is you do it through practice. The more you practice, the more natural the process becomes, and the more you see, here's things to be aware of, and here's why we want to do things in certain ways. So practice, practice, practice. Do as much as you can. If you're following along with the video, make use of the pause button. See a problem that you like, pause it. Try it out yourself first. See how far you can get. And then if you ever want to compare, that's fine, no problem. Just unpause, and we can see how we match up. Hopefully, the further we go, we'll start to agree more and more, which will be wonderful. And it's going to be a lot of fun. Thanks for coming, and let's begin. Our first problem. Find integral 0 to 1, integral 0 to 1, e to the 2x cosine e to the xy dx dy. Now, this says, wait, this isn't that tricky. Look at our bounds. 0, 1, 0, 1. That's a rectangle. That's a square. How hard can it be to change our bounds in a square? And the answer is, it's actually amazingly easy to change your bounds if you have a square. So, okay, do we want to change our bounds? Well, let's look at our integral. Do we want to integrate e to the 2x cosine of e to the x times y dx? I think we could make progress, but I worry it would be challenging. We'd have to do some integration by parts, probably have some substitution involved. It's not so clear that it would be pleasant to work with. So let's just try changing the order of integration first. Now, one of the reasons we change order of integration is to make the integration simpler. Now, you'll notice here there's two x's, so we're like, okay, if we integrate with respect to x, some kind of integration by parts, take a while, but there's only one y, so that makes it a little bit easier to integrate with respect to y first. So we say, okay, change the order of integration. Now, what happens? Well, when it's a rectangle, it's super easy to switch bounds, just and you're done. Because really, what do our bounds become? If you write them down as a series of inequalities, you get 0 less than or equal to x, less than or equal to 1, 0 less than or equal to y, less than or equal to 1, which if you switch, well, that becomes 0 less than or equal to y, less than or equal to 1, and 0 less than or equal to x, less than or equal to 1. That's why it's so easy to switch when we have rectangles. So we still have 0, 1, 0, 1, e to the 2x, cosine e to the x times y, dy dx. Well, when we integrate here, well, there's only one y. The integral of cosine will be sine. But we have to be a little bit careful here because of that e to the x. So we would have sine of e to the x y, and we'll have e to 2x in front. Then we have to divide by the e to the x. It's acting like a constant when we integrate with respect to y. So we'll write it in that format there. And we're going to evaluate from y equals 0 up to y equals 1. Those are our bounds, dx. Well, e to the 2x over e to the x, that's not so bad. That's e to the x. Now when you plug in 1, you get sine of e to the x times 1, so that's sine of e to the x. When you plug in 0, you get sine of 0, which is 0. All right, dx, and of course don't forget bounds. We're always doing definite integrals when we talk about multivariable calculus here. Well, you might think, integration by parts again, but wait, no, it's better. You see, what's the derivative of e to the x? It's e to the x. Up here, derivative of e to the x is not e to the 2x, so we have that sort of like extra coming in. But now, beautiful. If you let u equal e to the x, du will be e to the x dx. So this becomes, well, okay, plug in 0, e to the 0, 1, plug in 1, either one is e, and then sine of u du. Well, all right, integral of sine is minus cosine. So minus cosine of u evaluated 1 to e. So that's minus cosine of e minus minus makes plus cosine of 1. And we're done. Wow! That was even more beautiful than we probably would have expected. And probably would have expected like e's on the outside. But no, they all went away. Wow. Good. What a nice, fun warm-up problem. Now that we're warmed up, we can start tackling some more challenging, more fun problems, right? Of course. Yeah, let's go for it. So our next problem. Change the order of integration for the following integral. Integral 0 to 4, integral x squared minus 8 to 4 root x, f of xy dy dx. All right, well, let's think about what we have. So we pair things up. So our outer layer tells us that x goes from 0 to 4, because our outer integral is an x integral, x equals 0 to x equals 4. Then the next layer, that's our y integral, so x squared minus 8 less than or equal to y less than or equal to 4 square root of x. So we have to get a sketch of what this looks like. All right, so what do we have here? Well, y equals x squared minus 8. That's like the parabola x squared, but shifted down by 8. So if we say here's negative 8, down here, then we have this parabola coming up. And then we have, okay, what is 4 root x? Well, that's like square root of x, but it's been stretched by a factor of 4. Okay, so that's going to do that. Now, the question, okay, where are these things intersecting? Now, one thing that's helpful is to think about what's happening at the end, so at 0. So notice at 0, we're going from negative 8, which is down here. Let's make that negative 8 more clear. And here, 0. Okay, so when we plug in 4, what happens? 4 squared minus 8, 16 minus 8 is 8. Here, 4 times square root of 4, that's 4 times 2 is 8. Oh, so this intersection point actually matches up with where the bounds are. So that's a 4 and that's an 8. And so, in terms of how are we integrating, well, the order dy dx says, okay, as x goes from 0 to 4, for any choice of x, we go between the two curves. So currently we're set up to do nice vertical slices. That's how we're currently set up, and that's our region. We want to talk about changing our order of integration. Okay, great. Sounds like a good plan. Well, what do we do? Well, we're going to go from vertical slicing, which is dy dx, horizontal slicing, dx dy. And we should take a look and just sort of see what's happening and get a feel for it. And you'll notice, something's happening there at 0. Notice below 0, our left-hand curve is the axis, but above 0, our left-hand curve is this 4 root x. What does that mean? It means we're going to have to split. We're going to have two different integrals. Every time you have a change in behavior, you have to cut your integrals so that you always want to have a consistent left-right for every integral that you do. Well, we're almost ready to write it down. In fact, there's really just two more things we really need to identify, and then we'll be ready to more or less write down the answer. What are the two things left? Well, they are understanding these curves. So this curve here is y equals x squared minus 8. But we also need to think of it, what is x as a function of y? So that's not too bad. We could add 8 and say, x squared is y plus 8. or x is the positive square root of y plus 8. Now, why is it the positive square root? Well, because we're on the place where x is positive. If we'd been here on the left-hand side, we'd have taken the negative square root. This curve is currently y equals 4 root x. Well, you can also imagine, hey, that's the same as square root of x equals 1/4 times y. And if you square, you say, oh, that's x equals 1/16 y squared. So that's that curve, x as a function of y. All right, well, we're now ready to write down our answer. Here we go. We're going to do the bottom part first. It doesn't really matter which order you do it, but might as well work from top to bottom. So it's an integral, same function, that doesn't change, dx, dy. You say, okay, how does it do y? Well, think about where does y go in this bottom part? We're going from -8 up to 0. So -8 to 0. And now, if I know what y is, what does x do? I go from left to right. Now, here we didn't write it down, but this is x equals 0. So I go from 0 out to x equals square root of y plus 8. And we want to have the x equals form because these are x bounds. X equals something to x equals something. So 0 square root y plus 8. All right, add to that, okay, integral, and fxy dx dy. Okay, now here, where does y go from? Well, starting at 0 up to 8. All right, great. And now, how about x? Well, we're going to go left to right. The left curve is a function x is, in terms of y, 1/16 y squared. The right curve, x is a function of y, square root y plus 8. And we're done. Aha! Beautiful, beautiful. Really, the bulk of the work here is saying, get the picture and then decide how to rewrite it, right? How to break things up in a better way, or maybe at least a different way. Now, you might argue, oh, we'd rather do that integral because, look, that's only one integral. This is 2. And so 2 seems twice as hard. Well, it depends on the problem. And who knows? There's the function. Might say, look, one order is very preferable compared to the other. But for right now, all we're asked to do is change the order. And we did it. So, woohoo! All right, great. Well, should try some more problems. Okay. So, here we go. Change the order of integration and then find the exact value of integral 0 to 1, integral y to y to the 1/3, 4 times sine of 2x squared minus x to the 4th dx dy. Even if they hadn't told us to change the order of integration, we probably would have said, don't think we can integrate this with respect to x. But we could integrate it with respect to y. Let's change the order. The problems will kind of tell you if changing the order is good. The rule of thumb is if the integral becomes simpler to integrate with respect to one variable versus another, change the order. That's the mantra to have. Okay, so let's start by looking at what our region is. And so we match things up. We're told that y goes from 0 up to 1. Okay, that's not so bad. And then we're going from y up to y to the 1/3. So that says we go from x equals y to x equals y to the 1/3. Now, what would these look like? Well, here's y equals 1. I'll just put a little dotted line here. Y equals x. Okay, that's pretty simple. That's this line here. And y to the 1/3 equals x. Now, maybe that's not so easy to think about what that looks like, but if we think of y to the 1/3 equals x, we can say, hey, y to the 1/3 equals x is the same as y equals x cubed. I can take the cube of both sides. So that would be a cube comes and does something like that. Okay, so this is x equals y to the 1/3, also known as y equals x cubed. This is y equals x, also known as x equals y. And we see what's happening is that we're going from this left curve to this right curve. So our region that we're integrating over is kind of this small little sliver, a little tiny sliver of a region. That's our piece. And currently the way that it's set up is that because we're integrating in the order dx dy, well, we're thinking about our slices going like that. So we're going to switch and have our slices be vertical. All right, so we say, great. Now that we have our picture, we can actually figure out things pretty well. I will note, this is at 1. So this will become integral for sine 2x squared minus x to the 4th dy dx. And then we say, okay, where does x go from? As we go low to high value, 0 to 1. All right? And now how about y? So I imagine I have a particular value for x, and I want to go and say, where do I go between? Well, the bottom curve, the low value, x cubed. The top, the high value, is x. And remember, these are y bound, so I want y equals. So y equals x cubed, y equals x. All right, great. Well, we've done the change the order. We also have to find the exact value. So we have to carry out the integral. That's what it's asking us to do. Well, that's not too bad. Integral 0 to 1. Because when we integrate this with respect to y, well, there is no y. So when we integrate, this is acting like a constant. So we get all that times y. And we evaluate from x cubed up to x. And I should follow the habit. Just so I remember what I'm evaluating, this is y equals x cubed to y equals x. Because you might say, oh, wait, what am I plugging in? You might say two variables, it's not so hard to keep track of. What if you had 7 variables? It might happen someday, you never know. But that's why it's good to keep track. So this becomes integral 0 to 1 for sine of 2x squared minus x to the 4th. And when we plug in, we'll get x, subtract x cubed. All right, well, can we make progress? I suspect maybe. Now, the original integral, forget it, hopeless. But the new integral, okay, something's happened here. We've added some stuff. Now, the stuff might be just the right kind of stuff, the right stuff, so to speak. So, looking at this, we say, hey, what if we tried a substitution? Because maybe it looks like there's a hope here for substitution. So if you set u equal 2x squared minus x to the 4th, what would du be? Well, 4x minus 4x cubed dx. And I'm sort of like, whoa, there's a 4, x minus x cubed dx. All of that becomes du. It's like they wanted us to succeed. I think they did want us to succeed. So, what do we get? Well, plug in 0, 0 minus 0, 0. Plug in 1, 2 minus 1, 1. The 4x minus x cubed dx is du. The sine of 2x squared minus x to the 4th becomes sine of u. Well, that's something we can actually integrate. So the integral of sine is negative cosine. Yeah, be careful. It's one of those things. The integral of sine is negative cosine. It's easy to forget the minus. So, okay, minus cosine. Evaluate 0 to 1. So we end up with minus cosine of 1. Okay. Then subtract a minus. Okay, that makes it a plus. Cosine of 0. And cosine of 0 is nice, Cosine of 0 is 1. Now you might say, well, what about cosine of 1? Well, cosine of 1 is cosine of 1. It doesn't simplify anymore. That's as simple as it gets. But, cool. Wow, these are kind of, well, once you start doing a bunch of these get not so bad. And they have a very definite flow to them. We're trying to, we're starting to pick up that flow, right? Of course, keep practicing. The more we practice, the better we get. So here we go. Change. We have integral 0 to 1, integral minus cubed root of x to x squared of our function dy dx, and 1 to 2, 5x minus 6 to x squared f of x y dy dx, to a sum of two integrals where each is integrated dx dy. So we're swapping order of integration. So we currently have two integrals, and after we change the order of integration, apparently we'll still have two. Okay. Well, okay, what's going to happen here? Well, let's think about our pieces. We really have two integrals. We'll think of them as what happens on each one. Now, the nice thing is it's the same function, and so at the end, we can put pieces and move things around. I suspect what will happen is, well, let's draw the picture, and then we'll see. I don't want to get too far ahead of the problem. All right, so what do we have? The first integral, we say, well, look, the x bounds are the outer bounds. That says that 0 less than or equal to x less than or equal to 1. And then the y bounds, we are told minus cubed root of x. I can think of that as x to the 1/3 less than or equal to y less than or equal to x squared. Okay, all right, well, that's not so bad. We can sketch that. And so what do we see here? So we're only going 0 up to 1. Let's say here is 1. And we have y equals x squared. Okay, we know what that looks like. That looks like our parabola. And then here, minus the cubed root of x. Now, what does the cubed root of x look like? Well, it almost looks like if you were to graph x equals y cubed. And so it would turn out to look something like this. So y equals minus x to the 1/3. In some sense, it's not too critical to get it exactly right. We just know it's negative and it'll have some shape. Okay. So there's that part. And now we're going to add to that. We're going to go from 1 up to 2. Okay, so here's 2. And then what happens? Well, okay, let's pull out our other color here. So for 2, x goes from 1 to 2, and we're going from 5x minus 6 up to x squared. All right, so great. Well, that says we continue the x squared. All right, so we continue the x squared. It's going to go up quite a bit. That's all right. And what happens? We have 5x minus 6. Well, that's a line. And to help us get some intuition, we can say, well, let's just plug in at the points where we cross, right? Okay, so another, well, I shouldn't say cross, where we start and stop. At x equals 1, 5 minus 6 is minus 1, which turns out to be right there. And at x equals 2, 10 minus 6 is 4. Well, that matches 2 squared, so it's going to match here. So it's this steep line going up. All right. So there we go. We have y equals x squared, y equals 5x minus 6, y equals minus x to 1/3. And we should have marked with colors. So the first integral does it from 0 to 1. And then we had to do a second integral because there was a transition. At 1, we transitioned with the lower curve being a bounding part. Okay, so there's our picture. Well, now once you have your picture, the next step is to sort of mark interesting things. So, for example, points. This point up here is x equals 2, y equals 4. This point down here is x equals 1, y equals negative 1. Over here is the origin. On the curves, well, y equals x squared becomes x equals square root of y. Y equals minus x to 1/3. If you cube both sides and move the minus across, x equals negative y cubed. And then here, look, I can add 6 divided by 5. So I can, in other words, I can solve for x. X equals y plus 6 over 5. All right, great. So those are all our pieces, and we're ready to write things down. Now, before I was sort of humming and hawing like, oh, I think something might happen, I think something might happen. Let's talk about what does happen. Why do we have to have two integrals if we change from the vertical slicing, which we currently have, to horizontal slicing? Well, you'll notice that as we start moving up, lo and behold, there's a change in the behavior. In other words, the left bounding curve switches. And when you have a change in a bounding curve, that says, oops, we need to change our integral, so we need to split it up. So we have to cut our integral at 0. But the other interesting thing to look at is if you say, hey, it's not the case that this integral here becomes one of our new integrals and that integral becomes a different new integral. It's like, no. A little bit of this plus a little bit of that will go into one integral, and a little bit of this and a little bit of that goes into the other integral. So it's not just a one-to-one translation. It's when we combine pieces together and sort of cut things up, it's some of this and some of that combined gives a new part. So that's why we don't want to start, oh, let's just do this by itself. Let's just do that by itself. No. We have to see how everything fits together. But from here, we basically can write down our answer. We say, okay, we have an integral, our function, dx dy. Well, where does y go from in the first part? Start at -1 up to 0. -1 to 0. Where does x go from? Well, left to right, low to high. Minus y cubed, because these are x bounds, so x equals minus y cubed, up to y plus 6 over 5. Okay, that's the first part. Plus integral. We're going to go 0 up to 4 for our y. Oops, should have written down f of x, y, dx, dy. And now for x, left to right, low to high. And x equals square root of y to x equals y plus 6 over 5. That's it. Woohoo! We're done. Wow, good. Good practice in drawing regions. It is kind of annoying when you have to have multiple parts, but still, it's important to get into the habit so that we can handle these problems in the future. The more flexible we are, the more power we have. Power to us, right? That's what we want. Okay, well, let's keep going. More problems to do. On to our next one. All right. Well, rewrite the following as a single integral by changing the order of integration. Ooh, all right. So currently there are 3 parts. We want to get down to 1 part. Okay, well, all right. It doesn't seem so bad. How bad could it be? Famous last words. Okay, well, we do it 1 part at a time. Okay, so let's start by saying, here's our first integral. What does that do? Well, it tells us something about the bounds, right? Y goes from 0 to 1. And x goes from minus 1/2 square root of 4 minus y. and up to minus square root of 1 minus y. Okay, that's interesting. All right, well, we should try to get a handle on these graphs here in some way, shape, or form. Let's take these curves and solve for them not as x as a function of y, but y as a function of x, because we will need to do that if we're going to switch our order of integration. So if I start x equals minus square root of 1 minus y, if I square both sides, okay, x squared is equal to 1 minus y. Or we can write that as y equals 1 minus x squared. Okay, so 1 minus x squared would be a parabola that's been shifted up. So I'm just going to draw that in a little bit dotted here. And, okay, now this other curve, if we have x equals minus a half square root of 4 minus y, well, what would that do? Okay, x squared equals 1/4 times 4 minus y. All right, multiply by 4. And you can say 4x squared is equal to 4 minus y. Or we can say, oh, that's y equals 4 minus 4x squared. Okay, so it's actually very similar to the curve we just drew, just stretched up by a factor of 4. Okay, to stretch this up a little bit taller. All right, so it comes down and something like that. All right, so now that we have this marked, we can be more careful. So this right here is at 1, up here is at 4, and so we're going, y goes from 0 to 1, that's what we're told. The minus 1/2 square root of 4 minus y, that's this left-hand side, and this square root of 1 minus y, that's this right-hand side. So our shape is this piece. So that's the first integral. Okay, how about our second integral? Well, let's do that one. That's our second integral. Well, what would that be? So for our second integral, we would have that y goes from 1 to 4. So 1 less than or equal to y less than or equal to 4. And our x goes from minus a half square root of 4 minus y less than or equal to x less than or equal to square root of 4 minus y. But wait, we already have these curves. Whoops, I forgot a half here. Doop. See, the minus a half square root of 4 minus y, that's this curve. I'm going from 1 up to 4. And then here, we're going to have the positive 1/2 square root of 4 minus y. That's this left-hand side. So the second integral is this piece. All right, great. So there we go. There's our first two integrals. One integral to go. I think I see where it might be. Well, let's be careful though. What does our third integral become? So we have what? 0 less than or equal to y less than or equal to 1. That's our outer layer. And then our inner layer says square root of 1 minus y less than or equal to x less than or equal to 1/2 square root of 4 minus y. So, okay, so we're going from 0 to 1, so we're going here to there. We're going to go, the left side is the square root of 1 minus y, which is this curve. The right side is this 1/2 square root of 4 minus y. So it's this piece here. And we say, okay, so those are our three integrals. We say, beautiful, this is great, because we see what's happening here. We can see these curves. This intersects at -1 and +1 on the x-axis. This bottom parabola, we actually worked it out. This is the parabola y equals 1 minus x squared. And this top parabola is y equals 4 minus 4x squared. So what we get is an integral f of xy dy dx. Say, okay, x goes -1 to +1. And now, for any value for x, you go from the lower curve to the upper curve. Well, that's from 1 minus x squared, that's our lower curve, to our 4 minus 4x squared, that's our upper curve. And we're done. We're done. Now, it's kind of a cute little picture, and it makes you think a little bit. There's the Star Trek. They have the Starfleet insignia. So it makes you think, aha, you should do calculus so that you can live long and prosper. All right. Well, more problems to do, yes? Oh, yeah. Oh, yeah. Always more to do. On to our next one. Find the integral 0 to 1, integral arctangent of y to 1/4 pi, cosine of log of secant of x dx dy. Okay, yeah, we don't want to integrate this with respect to x. But integrate with respect to y, we'll integrate with respect to y all day. That's wonderful. We love integrating this with respect to y. So this is suggesting, hey, let's switch the order of integration. So at the very least, we can make some progress, and hopefully whoever grades it gives us partial credit, right? Well, I suspect more will happen if we change the order of integration. We're not going for partial credit. We're going all the way. So let's think about what's happening. So if we think about our bounds, what do we have? Well, 0 less than or equal to y less than or equal to 1. And then we also have arctangent of y less than or equal to x less than or equal to pi fourths. Interesting. Well, these aren't so bad. We can actually draw these functions. For example, arctangent of y, that's arctangent. It's a curve that's like one part of tangent, just turn on its side. And so there's our arctangent of y. And we're told we're going from arctangent of y over to pi over 4. Okay, well, what would that look like? So x equals pi over 4 would be somewhere like here. So here's pi fourths. Now the nice thing is, if you arctangent of 1 is pi fourths. So here's 1. Now my picture is a little bit off because if you actually compute pi over 4, it's actually smaller than 1. But okay, other than the fact that my picture is not great, but we have the right kind of setup, right? We see, okay, what's happening here? Well, we see that we have y goes 0 to 1, and x goes arctangent of y to pi over 4. All right. Now, we want to switch things. So, what can we do? Well, one thing that we can do is the following. Oh my gosh, this is embarrassing. Oh, I've been drawing the wrong picture. Okay, all right, cross that picture out. I was drawing y equals arctangent of x. That's not the right picture. What is the right picture? X equals arctangent of y. Now, what does x equal arctangent of y? If you look at x equals arctangent of y, well, that's the same as saying y equals tangent of x. So my picture was drawn in the wrong way. You should try to draw your pictures correctly. It helps a lot if you can draw things correctly. Okay, so that's, x equals arctangent y would look like this. All right, and then we're going over to pi fourths. Okay, so that's here. And if you plug it in, you do get 1. So what is the right picture? Well, as we have y going from 0 to 1, so here's y going from 0 up to 1, we go arctangent of y to pi 4. So that's the picture. That's the region. Okay, well, crisis averted. We were on track to be flummoxed in a minute here. Well, no, you were doing great. It was me. I was the one like, ah. All right. Well, okay, so now that the picture is drawn, okay, x equals arctangent of y. Well, it's the same as y equals tangent of x. And we say, hey, wow, beautiful region, right? Because what does our region become? That says we're going to get integral, same function, cosine, log, secant x, and we're integrating dy dx. And we say, well, x goes from 0 to pi over 4. Nice. It's always nice when you get 0 involved. And then where does y go? Well, it goes from 0 up to tangent. So 0 up to tangent of x. All right, great. Well, what does this become? Integral 0 to pi over 4. When we integrate the inside, cosine log secant x times y. And evaluate y equals 0 to y equals tangent of x dx. Now, plug it in. Well, plug in 0, you get 0. Plug in tangent of x. So we end up with the integral 0 to pi over 4 cosine of log of secant x times tangent of x dx. Now, can we integrate this one? Well, yes, we can. Now, it looks bad, but look at that tangent of x. This is one of the things that often happens when we have these types of problems like, oh, we couldn't do it before, but now we can, because the new piece that we've added on the outside is just what we needed, just the missing gap. So notice if I start with saying log secant as u, what's the derivative of log secant? Do you remember? It should sound familiar. Log secant should be like, ooh, I've heard this somewhere before. It's something. It is. The derivative of log secant is tangent. So that would become du. So what do we have? Well, okay, this is the integral. We've got to update our bounds. Plug in 0. Secant of 0, 1. All right. Log of 1 is 0. So 0. That's nice. Secant of pi fourths is square root of 2. Okay. Log of square root of 2 is, log of square root of 2. We really can't do much for that. It is what it is, as they say. And then we have cosine u du. Well, hey, that's integral of cosine is sine. So sine of u from 0 to log of root 2. Now the nice thing is sine of 0 is 0. So we end up with sine of natural log of square root of 2. Done. Wow. Other than that silly mistake at the beginning, that wasn't so bad. Now, we would have discovered the mistake because we would have gone to a point like, oh, wait a second. We can't do this. Something terrible has happened. And then we would go back and start saying, what did we do? And, all right. So, check your work, be careful. But if you find things are going bad, this is a great piece of advice. If you have a problem and you're like, wow, things are getting out of control here, stop and go back. There's a natural tendency to say, no, I've already bought in. I think some people might call this the sunk cost fallacy. It says, no, look, I've already invested too much. Even though it's a wrong thing, I can't give up now, so I'll keep moving forward. And that's a bad approach, because if you have an error, and if you say, no, I'll keep moving forward, your error starts to snowball out of control, and you don't want that. So what should you be doing? Instead, you should say, okay, look, I know I invested some time, but if I keep going, it's even more wasted time. Let me go back and just make sure I haven't made a mistake before. So keep that in mind. Be willing to look back and see what you did. All right, well, good. More problems to do, so let's keep going. On to our next one. Find the integral of the function f of xy, which is cosine of y cubed, over the region bounded by, then we have some various curves. Okay, so let's see, what do we have? Y equals 2 square root of x. Okay, so that's the square root of x function that's been scaled. 2 square root of x. We have, I probably drew this in the wrong way. X equals 0. And here is x equals 8. So there's our picture here. And so as you can tell, I did not plan ahead very well, because that 2 square root of x is on the inside, but that's all right. All right, so we have this sort of triangle, well, except one side is a little bit curved, but, essentially triangle-esque shape. Okay, so here's our region, and now notice it says just find this integral. So find this integral over our region of cosine y cubed dA. So we have to decide. Now, in other words, do we do dx dy or dy dx? The only way we do integration right now is iterated. Now you can say, let me use the picture to give me a suggestion, or let me use the integral to give me a suggestion. Either way, you should come up with the same answer. We want to integrate with respect to x first. Okay, why? Well, let's do it in terms of the function. If we integrate with respect to x first, there's a chance. If you integrate with respect to y first, hopeless. Forget it. Forget it. Can't be done. Can't be done. All right, so let's integrate with respect to x first. All right, so integral cosine of y cubed dx dy. Now I said there's the function, tells you integrate with respect to x first, but there's also the region is suggesting integrate with respect to x. It's a weaker suggestion, but if you think about what's happening, if you do dx dy, that's your horizontal slicing. If you do dy dx, that's vertical slicing. And if you look, you say, hey, if I do horizontal slicing, one of my bounding curves is 0. I like 0. 0 is a friend. And so as soon as you can get 0 in, do it. So that's why, if we integrate dx dy, I can get 0 on the inside. Whereas if we did it as dy dx, no, forget it. Hopeless. Can't do it. Now we have y equals 2 square root of x. Well, we need to solve for x. And so we could say y squared equals 4x. Or we could say x equals 1/4 y squared. Now, whoops, I wrote x equals 8. That should be y equals 8. Sorry about that. And, okay, great. Now, we're ready. Let's talk about our bounds. Where does y go from? Goes from 0 to 8. Easy. It's almost like they gave it to us because they gave it to us. Where does x go from? Goes from left to right, low to high, from 0 to 1/4 y squared. Remember, these are x bounds, so we want x equals something. So 0 to 1/4 y squared. All right, so this is going to become integral 0 to 8. We can integrate with respect to x, no problem. So saying y cubed x. Evaluate x equals 0. X equals 1/4 y squared dy. And, we plug this in, and we say, look, this is going to be integral 0 up to 8. And then we're going to have cosine of y cubed times 1/4 y squared dy. And now, hey, what? Almost like it had been planned to happen, because of course it was planned. Of course it was planned. So what do? All right, make a substitution. U is y cubed. Well, what does du become? Du becomes, well, 3 y squared dy, or 1/3 du is y squared dy. All right, so we end up with, well, 1/3 times 1/4 will give us 1/12. So this 1/4 y squared dy will become 1/12 du. And then we have the integral. We have the 1/12 cosine u du, and then we have to evaluate 0 up to 8 cubed. And 8 cubed is a number. You can write it as 8 cubed, or if you really like, let's see, what would 8 cubed be? That would be 512. Okay. Well, if you think about 8 cubed, it's really 3 2's, right? So when you have 8 cubed, it's like you have 9 2's. So you just do your powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, 512. Okay, so 0 to 512 cosine u. All right, well, great. That's 1/12 sine of u from 0 to 512. And if you plug in 0, you get 0. And so we end up with sine of 512 divided by 12. Done. And wow, what a crazy number. But you know what? Sometimes that's the way things work out. Things may not always work out as super clean numbers. You just follow it along and see where the process takes you. And good. Well, all right, we're getting the hang of these. We might even be getting good at them. Of course, we'll only know if we do some more practice, right? More practice. Okay, our next problem. Like I said, we're going to get really good at these kinds of problems because we're going to have so much practice. Find the integral 0 to 1, integral x squared of x, 30x times cosine 5y cubed minus 3y to the 5th, dy dx. Well, okay, by this point, we should be really comfortable. So we think about the bounds. What do they translate into? We're told x goes from 0 up to 1, and y goes from x up to square root of x. So in terms of a picture, okay, y equals x, and then we have y equals square root of x. And lo and behold, they do both intersect at 1. So there we go. There's our region. And we look at this and say, integrate with respect to y. No, we don't want to do that. Integral with respect to x. Now, there is an x there, but it's an integral that we're okay with. We wouldn't mind integrating with respect to x here. So, all right, what do? We say we'll change the order of integration and say this will be the same as integral, same function, that doesn't change. And then what? Well, it's going to be dx dy. So, in particular, we're now changing to horizontal slicing. Where does y go from? Low value to high value, 0 to 1. Where does x go from? Well, from left to right. So we have to think about what these curves are. Now, the right-hand curve is pretty easy. Y equals x, x equals y. The left-hand curve, y equals square root of x, that says x equals y squared. So 0 to 1, y squared to y. So integration, well, the integral of 30x, because this cosine 5y cubed minus 3y to the 5th, that's a constant. So that would become, when integrated, 15x squared, and then the cosine piece here still is the same because we're integrating with respect to x. And evaluate x equals y squared, x equals y dy. All right, well, that's 0 to 1 of, well, 15. And then plug in x equals y squared minus, plug in y squared squared, y to the fourth. Cosine 5y cubed minus 3y to the fifth dy. Now, at this point, we're like, what can we do? Well, we know what to be looking for. Like, hey, now that we integrated once, maybe this extra stuff is enough to help us handle that inside part. So we're thinking, let's see if we can do a nice substitution here. Well, let u equal 5y cubed minus 3y to the fifth. Then what do we end up with? du would be 15y squared minus 15y to the fourth. Oh, wait, that's not just anything. 15y squared minus 15y to the fourth dy is exactly what we have written down. So this is going to become, all right, our bounds, 0, 0, okay. Plug in 1, 5 minus 3, 2. Then we're going to get cosine u, and then the rest of it becomes du. Wow, beautiful. So integral cosine, positive sine, and evaluate 0 to 2. If you plug in sine of 0, you get 0. And so we plug in 2, and we end up with sine of 2. And we're done. We're done. Wow, great, nice. Okay, so yeah, once you get the hang of these problems, they go pretty quick, right? All right, well, let's do one more problem. One last problem to finish it up. And this one was a interesting problem that comes from an old exam. And I'll tell you, I wrote this one. I had a lot of fun. And the students were really like, ah! And then they saw the answer and they're like, oh! Okay. But let's begin. So we're going to find the integral 0 to 1, integral x up to cubed root of x, 24 times the square root of 1 minus y to the fourth dy dx. And, okay, looks pretty harmless. But we see, all right, look, can't really integrate this with respect to y, so we'll swap the order of integration first and integrate with respect to x. Same procedure as before. So we think about our bounds, and what do we see? We see x goes from 0 to 1, and then for y, we go from x up to the cubed root of x. All right, well, great. What would that turn out to be? If we draw our picture here, well, y equals x, that's pretty easy to draw. And then here, think of y equals the cubed root of x. Well, that's not so bad either. Cubed root of x does something like this. And they happen to intersect at 1. And so our shape is this sliver. Now, we should mark these not just as y is a function of x, but x is a function of y, because we anticipate we're changing order of integration, since that's what we're doing. And here we'll have x equals y cubed. Okay, great. So what do we get? Well, we see, this will become integral 24 square root 1 minus y to the fourth dx dy, because we're switching the order of integration. Where does y go from? Low value to high value, 0 to 1. Where does x go from? Well, if I add a particular value for y, from low value to high value, left to right, from x equals y cubed to x equals y. And so there we go. Great. Wonderful. So this is integral 0 to 1. And, well, we can integrate that because there's no x. Square root 1 minus y to the fourth times x, evaluate from x equals y cubed to x equals y dy, which is the integral 0 to 1, 24 square root 1 minus y to the fourth times y minus y cubed. All right, Great. Now, at this point, we're like, aha, we'll do our old standard trick, because it always seems to be what happens. We'll let u equal the inside, and then du is not that. Oh. Huh. Uh-oh. This is different. Something's weird here. How are we supposed to do this one? Well, we start going, what can we do? What can we do? And, well, we're not going to give up. That's not our attitude. We're can-do people. We can do this. We just have to think about what's possible. Now, we can see something, right? If we said, well, if we did set u equal to the inside, what would we have? Well, the derivative of 1 minus y to the fourth is minus 4y cubed. And we say, well, there is a y cubed there. That's something. And so, really, we do have a way to handle, if it was just the y cubed, life would be okay. So here's something we can do. This is a really cool trick called expand. And so, and I'm going to combine it in a second with another cool trick. But first off, we can think of this as, all right, as 24y square root of 1 minus y to the fourth, and minus 24y cubed square root of 1 minus y to the fourth. And the other cool thing is called separate. See, what you can do is you can say, hey, I really have two pieces. It might be the case that I need to use different ideas on each part. So don't get into the habit like, oh, if I have an integral, if I'm using one idea, I have to use that idea for everything. See, sometimes integrals break into pieces, and oh, this part will have one idea. This other part, I might need a different idea. And so we have to be flexible and say, well, let's think about what we could have. 24y, 1 minus y to the fourth, dy minus integral 0 to 1, 24y cubed, square root of 1 minus y to the fourth, dy. So let's talk about our two parts. Let's do the last part, because we said, hey, this fits really well with what we think should happen. So we'll let u equal 1 minus y to the fourth. Then we'll get du is minus 4y cubed dy. Now, notice we have a minus here, so I can move this plus and then make that to a minus 24. And really, I can go even further and say, hey, this is really minus 4 times 6. So, if we update, what do we have? Well, we have the following. We have the integral, and our bound will be 1 minus 0, which is 1, 1 minus 1, which is 0, and then the minus 4y cubed dy makes that a du, and then we have a 6 square root of u, or if you like, 6u to the 1/2. Well, that's not so bad. We can actually integrate that. If you integrate, well, that's 6. U to the 1/2 is u to the 3/2. We have to multiply in front by 2/3 and evaluate 0 to 1. Well, 6 times 2/3 is 4. Plug in 0, you get 0. Subtract, plug in 1, you get 1. So we end up with minus 4. Okay, so that's the contribution from the second part, minus 4. All right, great. But we have a first part. We can't do the same thing. But maybe we don't have to do the same thing. Okay, see, what's wrong? In the first part, if I try to let y to the fourth, there's not a y cubed out here. There's just a y. You say, okay, well, what can you use so that you get the derivative that looks like y? And the answer is y squared, does it? Okay, so let's try that. Let's let u equal y squared. Now, you might say, okay, well, certainly the good news is that it works really well in terms of the du. So we get du is equal to 2y dy. And now we say, well, look, 24 It's really 12 times 2. So we can write this as the 12 is a constant can pull out. Integral 0 to 1. 2y dy is du. And now we have the square root of 1 minus u squared. How do you integrate that? We don't have to, because we should recognize it. This is not just anything. The square root of 1 minus u squared is what? It's a quarter of a circle. So we say we can interpret this as being the area of 1/4 of a unit circle. So that integral is 1/4 of pi. So this turns out to be 12 times pi over 4, which is 3 pi. And therefore, we put our pieces together. In this one, we did one substitution y squared. Over here, we did a different substitution, 1 minus y to the 4th. In both, we were able to carry it out. So our final answer is 3 pi minus 4. Done. Done. This is a fun problem. And of course, when you're not in the middle of a test, it's really fun. But I think what happened is people are kind of in the mindset, we only should be looking for one technique at every step. And it's like, no, not necessarily. You always should think about integrals as saying, let me think about the problem I currently have. And let me see, can I do a part of it? And if you can, okay, break things off into parts that you can do. And you may not necessarily do the same thing for each part. So be flexible. Be open to the possibilities that there are many different tools. And you might have to use both a screwdriver and a hammer to solve this particular problem. Who knows? I really love this problem. Because you see the answer and you're like, but it's not always clear when you're going through it. Okay. Well, a great place for us to stop. Thanks for coming in and doing the practice. Hopefully by now you're really comfortable by changing order of integration, because we've done a lot of them. And of course, there's infinitely many more you could do, but this gives you a really nice flavor of the type of problems you might see. All right, take care.